Let's investigate a question that's quite a bit easier than what we usually investigate. So this is a question we could solve without using any computer simulations, but we're going to start out with a computer simulation, and then we're going to talk about the dangers of overfitting based on that computer simulation. So here's the experiment we want to run. We're going to roll X six-sided dice and add up the values, and then we want to know what's the expected outcome. And I can tell you what the answer is supposed to be. Well, it's going to be X times the expected value for one die roll. Okay, and the expected value for one die roll is 3.5. Okay, if you add up 1 through 6 and divide by 6, you get 3.5. And so the answer, the exact answer is 3.5 times X. Okay, but let's try to get this using a computer simulation instead. So first I want to say how many experiments are we going to use. So let's have n stand for the number of experiments. And let's use a small number because this is a basic problem we're investigating. We don't need very many experiments to get an accurate answer. So let's take n equals 10. And notice that I'm not saying roll 5 six-sided dice. I'm saying roll a variable number of dice. So that makes it a little bit harder. So what should we choose for X? Well, let me give a maximum bound of 15. Okay, so at most I'll use 15 six-sided dice. And as a minimum, I'll use 1. And okay, well, just like always when we have a number of experiments, we're going to put those experiments inside a for loop. So for I from 1 up to n. Okay, and here let's choose X equals rand I 15. Okay, so that's going to stand for how many dice, and it's going to be a randomly chosen integer from 1 to 15. And I want to keep track of the data, so let me make a data array. It's going to be 2 columns and n rows, but let me start out with just an empty array or an empty vector. And so now I've decided I'm going to roll X dice. So for example, if X is 7, I'm going to roll 7 dice. And so now let's do that part. So let's say Y is going to be some rand I. Okay, they're going to be 6-sided dice, so this is always going to be a 6. And then I want to roll X of them. Okay, so this is roll X 6-sided dice, and then add up the values. Okay, and that's going to be Y. And then I'm going to put this as a new row inside my data array. So data array, we're going to just append this onto the end as a new row. So I don't want to use a comma here. I want to use a semicolon to get a new row. And then I'll put X comma Y. So let's just run this and see how it looks. So I'm going to save this as dice script. And let's look at data array. Okay, so here we rolled 4 dice and got a total of 13. Here we rolled 14 dice, got a total of 49, and so on. And secretly, we know that the best approximation for the relationship between column 1 and column 2 is that column 2 will be approximated by 3.5 times column 1. But we want to see if we can find that using MATLAB and using these experiments, okay, rather than the theoretical computation that justifies that 3.5. So how can we get this? Well, let's use, how about, I could use fit LM, but I eventually want to go to a higher degree polynomial. So let me just start out right away using polyfit. And remember, polyfit takes the independent variables X, the dependent variables y, and what's the degree going to be. So in this case, let's use the correct degree of 1. So let me choose x1 equals data array. And I want to have this to be the first column. So every row in the first column. And y1, okay, same thing, but in the second column. So this will be x1, y1, maximum degree of 1. And we'll call this p. Remember, this is going to be a vector corresponding to the coefficients of the polynomial, starting with the leading coefficient and working our way down to the constant coefficient. So in this case, it'll be a length 2 vector. Think of it as like m comma b in the usual mx plus b formulation. And let's plot this stuff. So we're going to plot x1, y1, and let's use O's to mark those. And then let's also plot what we get from the polynomial. So we get x1, and now we want to evaluate the polynomial p at the inputs x1. So we'll do that using polyval for evaluate the polynomial, p x1. And let's just join this data here using the default connection. So I'm not going to specify anything with a string after this part. And let's save it, and let's see how this looks. Yeah, looks great. But in the next video, we're going to see what the dangers are, the possible pitfalls are of this kind of process.